Okay, good morning, everybody. Good morning. Hope you're having a nice Saturday morning. Thanks for coming back, despite the rain. We're stuck somewhere in the 17th century. And last time we have already covered many things. We've started in antiquity. We've seen how heat has been used for little gimmicks, like this altar where water was sort of pushed up and out through the arms of these figures. We've also seen how heat made its way into medicine, how at the beginning temperature and the temperament of a person started being linked. We've also seen how heat became something you can measure, or temperature became something you can measure. We've seen the first thermometers appear and how that gradually evolved into a lot more precise instruments that were very useful. And again, one of the main early uses of thermometers were in medicine. We've seen how physiology and the study of the metabolism emerged as a result. And we've also seen how people started appreciating that heat was something a lot more subtle and involved than they had previously appreciated. We've seen how thermometers can measure temperature, but that if you put a cold object next to a hot object, the temperatures will eventually be the same, but it is heat and not temperature that makes that be the case. Okay, our hero there was Joseph Black, who sort of invented the notion of sensible heat. If you can touch an object and it's warm, you can sense it, then that object has a certain amount of sensible heat. And in fact, he also invented that concept that there is a certain capacity for a sensible heat, that it's inherent to an object and determines how much heat it can store. And then we've also seen how Black went beyond this first great accomplishment of his, and he also discovered that there is more than just sensible heat. There's an entire different kind of heat that he called latent heat, and that is not showing up as a change of temperature, but that is required if you want to melt ice or if you want to boil water. It requires a large amount of heat that does not go into a change of temperature, but goes into a change of the state from a solid to a liquid or from a liquid to a gas. And we've also seen, sort of entirely parallel to this entire development, how heat found its use in engineering. We've seen Captain Savory and his miner's friend, the first steam pump, and we've seen Thomas Newcomen and his atmospheric engine, both of which eventually led to the catalyzation of the early Industrial Revolution, which had a great impact upon many, many people. And so now, with the benefit of the hindsight that we've built up, looking back at the story, we can sort of see, how things progressed, starting from some very vague and unclear notions about what heat is and what it can and cannot do, to at least being able to quantify that ignorance by having an instrument that allows you to go beyond what your senses tell you, to eventually, with Joseph Black, coming up and inventing some narratives and explanations for what's going on in your measurements. But we've also seen that this entire engineering storyline sort of set a bit to the side and wasn't really talking much to what the scientists did. Now, our question for today, in fact, is to answer that question that we set out 2 weeks ago, namely, what is the nature of heat? And as we're going to see, it's both of those sides that will today become unified and eventually lead us to the answer to that question, the science and the engineering. And to start with that story, we need to go back to Glasgow in the 1700s, mid-1700s, where we've seen last time Joseph Black, as a professor of anatomy, doing all of these experiments and interpreting the experiments that then led to sensible heat and latent heat. Now, there was another person who was at the University of Glasgow at exactly the same time as Black was, and that person is James Watt. Now, James Watt was born in Scotland, went to London as an apprentice for a mathematical instrument maker. Now, that's a profession that today doesn't exist anymore, but back in the day would have meant that you build instruments that are used primarily on ships, seafaring instruments such as a mariner's compass, important for navigation, or a quadrant, an instrument like this where sailors could measure very precisely the angle of the sun above the horizon of the sea, again, very useful for navigational purposes. Now, apprenticeships to this profession were very strictly regulated in these times. It would take 7 years of training to become an instrument maker. Watt did it in 1 year. After completing he was an extremely capable artisan. He could build extraordinary instruments very, very precisely, and he completed his 7-year training in a single year. And then he went back to Glasgow, but because things were so strictly regulated, it was difficult for him to find a job. People didn't want to hire him because they saw he had only 1 year of training. They were expecting 7. Now, eventually, he got appointed as a mathematical instrument maker to the University of Glasgow, who did not have to abide by the regulations. The university had the luxury of being able to hire him because they recognized his capabilities as an instrument maker. And so, he was at the university at the same time as Joseph Black was, and as he recalls, in the winter of 1763 to 64, he was given a model of a new common steam engine to repair. Now that's a small model engine that they would use in lecture demonstrations at the university. And you can see it has all of the elements of a new common steam engine that we saw last time. There is a boiler, there is the piston, there is the beam that would sort of rock back and forth, and there would even be a small little pump to demonstrate to the students that these things could be used as steam pumps. Now that machine was broken, so James Watt set out to investigate what was happening, and in fact what he saw is that the model engine would take a few strokes and it would then stop. Okay, it wouldn't run continuously, it would seem to start up, do a few strokes and then stop. And he was very surprised to find, as he says, that the boiler apparently, while producing loads of steam, didn't produce enough steam to keep it running. Okay? And so, being the very methodical and very careful investigator that he was, he set out to investigate what was happening. Okay, so what's the origin of that apparent heat loss that prevented the small boiler of the engine from really powering it through? And he focused his attention on that one part of the stroke of a new common steam engine that we already saw last time, where after filling the piston with steam to make it fully extended, you would then inject cold water to condense the steam and to make the atmospheric pressure outside push the piston back in. Okay, that's the most important part of that stroke because that is, according to an atmospheric engine, where the actual power is produced. And of course, his model steam engine would also have that, would also use that part of the stroke. There would be a cold water injection into the hot piston. And so, James Watt set out to measure everything. Okay, he measured very carefully how much steam would be needed to fill the piston in the first place, or in his words, how much water he needed to evaporate to produce the steam to fill the piston until it was full. And then he would also measure, with a full piston, how much water he would need to inject to condense that steam back to water. Okay? And he would find, as he says, he was astonished at how much water he would have to inject to actually condense that steam back. In fact, he found that the amount of water he needed to inject was a lot greater than the amount of water he had to evaporate beforehand to produce the steam. Okay? So he says, apparently, there is some great heat that the water he injects had acquired from the small quantity of water in the form of steam which had been used in filling the cylinder. Now, if you think back to what we saw last time, this is exactly Black's idea of latent heat. To produce that steam that goes into that piston, you have to produce a large amount of heat that goes into that steam, not as a form of temperature, but to make that water boil and convert it into steam. So that entire heat is still stored by the steam, and it's that full, large amount of latent heat that the cold injected water will have to absorb to make the steam go back to water. And that's why he needed so much water. But he was very confused. And he says, being struck with this remarkable fact and not understanding the reason of it, I mentioned it to my friend, Dr. Black. So there were these two people. They obviously knew each other. In fact, they were even friends. And in fact, Dr. Black then explained to me his doctrine of latent heat, which he had taught for some time. Okay, so Black had it all figured out. He was even given lectures on that subject. And James Watt, from a totally different angle, stumbled upon the same fact. Only then did the two start talking about this very subject, at which point James Watt was happy to find that everything is understood already. But then he went on and he encountered another sort of engineering dilemma, and that is, how much water did you actually want to inject into your piston? Because it's not obvious. There's two different considerations you need to carefully balance out, he says. On the one hand, you want to achieve a condensation as complete as possible of the steam, so as to produce a vacuum that's as complete as possible, and to give you a very powerful stroke of the engine. Okay, so that, from that perspective, you want to inject a large amount of water into your piston. But on the other hand, you want to keep the piston as hot as possible, because after condensing the steam, you want to put fresh steam back into the piston so you can start the next cycle. And if you have previously put in a lot of cold water, it will cool down the entire piston, and then you will need a lot of steam to heat that piston back up. And that will make the machine very, very inefficient. So from that perspective, you want to minimize the amount of cold water you inject. From the other perspective, you want to maximize it. So there's this tension between two things that cannot be true at the same time. And that is what James Watt found. He says, it also appeared that throwing in large quantities of injection, so as to form a good vacuum, would cool the cylinder too much as to require quantities of steam to heat it again. Now, in the words of his friend Joseph Black, who would have probably said that it's the heat capacity of that metal cylinder that complicates your life. Because if you want to heat up and cool down that large amount of metal that makes up your cylinder repeatedly once every cycle, you need to cycle back and forth a large amount of sensible heat in the form of steam, and that means in the form of coal that you have to burn to produce that steam. And so Watt sat down and he says, okay, what can we do? And he says, in order to make the best use of the steam, it was necessary for two things to be true. First, that the cylinder should be maintained always as hot as the steam which entered it. Okay, that's sort of clear. You don't want to be able to cool up and down, warm up and cool down that cylinder repeatedly. You want to keep it as hot as possible, such that the new steam you put in stays as hot as the cylinder already is. But that secondly, that when the steam was then condensed, the water of which it was composed and the injection itself should be cooled down as much as possible. Okay? So on the one hand, Watt says you want the cylinder to be as hot as possible, but you want the condensation, water and condensed steam to be as cool as possible. Now that's just saying that he wants to have the cake and eat it also. And as he says, the means of accomplishing these points did not immediately present themselves. But one day in 1765, a year afterwards, it occurred to me the following fact. Okay, he has a great idea. He says, if a communication were opened between a cylinder containing the hot steam and another vessel which is kept very cool by an injection permanently. Okay, so imagines, why do I have to have the hot steam and the condensation happen in the same cylinder? Why can't I have them in two separate places? I have a piston that's kept hot all the time. I have a separate vessel that's kept cool all the time because this is where my cold water is flowing in. And I have a pipe that connects the two. And I put a valve in that pipe, and that is what he means when he opens a communication between the two. Because if he does that, that hot steam from the hot piston would immediately rush over to the cool vessel, okay, immediately rush into the cold, empty vessel, where it would then be condensed, and the piston, of course, would follow the same cycle as it did in the Newcomen engine. So Watt's great idea was to separate the places of hot steam and cool water. And that place of cool water we now call a condenser, because this is where the steam is condensed. So the piston always stays hot and the condenser always stays cool, and you don't need to heat up and cool down repeatedly a large amount of metal. And that is a great advantage. And Watt recognized that it was a great advantage, because he says, when once the idea of the separate condensation was started, in the course of 1 or 2 days, the invention was complete in my mind. Okay, so once he has had that crucial idea, everything else fell into place very, very rapidly. And immediately he sets out to do an experiment to verify whether it actually works in practice. And so he builds a small prototype engine. And he takes out a patent. Okay, he was granted the patent in 1769, a few years afterwards. The title of the patent was A New Invented Method of Lessening the Consumption of Steam and Fuel in Fire Engines. Because that's exactly what his invention did. Because you don't have to heat up and cool down large amounts of metal all the time. You can make do with a lot less fuel. And your engine becomes a lot more efficient. So now he has a prototype, he has a patent, how to scale up and actually put this machine to use. Now Watt says of himself that he would rather face a loaded cannon than settle an account or make a bargain. So he was not the best person in charge of a business. So he needed a business partner. And the person he partnered up with was Matthew Boulton. He was an industrialist from Birmingham, a city with a lot of heavy industries in the middle of England, who was actually running a factory producing small metal goods, like buttons and belt buckles and such. And his factory would be powered by a water wheel and a small mill stream. And in the winter, where there is not a lot of water running down that mill stream, his factory would not have enough power due to the water wheel. So he was looking for an alternative to power his factory. And of course, he recognized the potential of James Watt's steam engine. And so he was very wealthy, and he was able to partner up with James Watt, and the two of them founded a firm by the name of Boulton and Watt. And they would build these steam engines. And later, they would hire this gentleman, William Murdoch, as an engineer who proved to be an extremely capable and innovative employee. He later on was made a partner in that firm, together with Boulton and Watt. And he would then later on go forward and invent the first steam locomotive. Okay, he's a really inventive person. So the three of them really set out to conquer the world, if you will. And that's the machine that they came up with and sold. And already by looking at that, you will see that it's a lot more complicated than that old engine by Newcomen. Okay, so it was a lot more tricky to build, but it was also a lot more efficient. And in fact, it contains a lot of wonderful engineering marvels, so let's have a brief look at what there is in that machine. There is, of course, the crucial parts of a steam engine. There is the piston that we always have, and down there is the condenser. So the piston is always hot, the condenser is always cool, and the steam rushes between them. There's also that beam that we know from the Newcomen engine that would be moved up and down by that piston. But in that case, they already put in a flywheel. Okay? For pumps, you sort of can make do with an upwards and downwards revolving motion. But if you want to power a mill or a general factory, you needed rotary motion. Okay, so they put in this large flywheel, and they needed a mechanism to translate that up and down motion of the beam into the rotary motion of the wheel. And they also needed a way, because a factory runs, if you will, at a steady speed of the wheel, they also needed a mechanism to keep the speed of rotation constant. And so they added this centrifugal governor. Okay, if you can imagine, this is something that's coupled to the rotary motion of the wheel, and it turns like that. And you have these two metal balls that if the rotation is too rapid, they would be pushed outwards by the centrifugal force. And then, because of them being pushed outwards, there is an intricate mechanism by means of levers and rods that would then close the steam valve. So the machine would turn slower again. Of course, if it turned too slowly, the centrifugal force would be not enough to keep the balls flying apart, and then the steam valve would open again. Okay, that's a feedback mechanism that kept the machine running at the same speed, irrespective of whether machines were turned on and off in the factory, and the load on the machine would be greater or less. Now, there is another sort of crucial part that also has a fun story associated to it, which is the sun and planet gear. So how did they actually translate that up and down motion of the beam into the rotary motion of the wheel? They did it like this. They took two cogwheels, and you can see the animation here. Here's the beam moving up and down, and here is the flywheel, and it's the teeth of the two cogwheels that would transmit the force, the momentum. Now you can, this was actually an invention by William Murdoch, that person that they hired, the right one on that statue. So you might think, why did they come up with such a sort of complicated mechanism with two cogwheels and such if they could have simply added a crank to turn the wheel? Well, it turns out somebody else had the idea to put a crank on a Newcomen engine, and that person was James Picard, and he also had a patent on that idea. Okay, he had a patent on a Newcomen engine or any steam engine with a crank turning a flywheel, and he patented it to full generality, okay, for any application. Boring iron, forging metal, rolling, flattening, and slitting iron, turning corn, even grinding corn. So to avoid having to pay license fees to Picard, they needed something that is not a crank, but could still transmit the up and down motion of the beam into the rotary motion of the flywheel. And this is why Murdoch came up with that planet and sun gear. In fact, once Picard's patent expired, they immediately abandoned it and went back to the crank, which was a lot easier to manufacture. So it was really just, on their economic interest to work around this. So that's the machine that they invented, and there's a lot more to be said about it. For example, how the piston that moves up and down is coupled to that beam that sort of rotates, or how it's made, how you can make sure that the condenser would keep condensing the steam indefinitely, and there's a lot more that we can discuss if you want afterwards. But at the end, the upshot of this is that their improved engine, which is a lot more complicated, only is a lot more fuel efficient. It only needed a quarter of the fuel of the Newcomen engine to do the same amount of work. You have a 75% gain in fuel efficiency. And so they knew that this was their biggest advantage, their biggest advantage over their competition. And so they didn't charge their customers to put up the engine. They charged their customers throughout the life of the engine by asking for a certain percentage of the fuel savings. Okay? And that meant that because the engine was very expensive to build, it only really made sense at the beginning to put it up in places where fuel was expensive. That you couldn't afford to run a new common engine, which was a lot cheaper to build but consumed a lot more fuel. And what they did was that steam engines started conquering remote places where there wasn't a lot of coal or where access to fuel was otherwise restricted. In other words, Watt and Boulton, and also Murdoch, they put steam engines everywhere. New common engines were confined to where coal mines were, where coal is plenty and cheap, but in very remote places without access to fuel, now the Industrial Revolution could also grab a hold. And that is primarily due to the fuel advantage of the Watt and Boulton steam engine. So that was a great and important advancement in the Industrial Revolution. Things could spread, manufacturing could spread, or otherwise it wouldn't have been able to. And this was the backdrop of the time. And this was also the time when people started thinking more and more carefully about what heat actually was that drove all of those steam engines. So let's pause for a second in our story and let's think about what people thought about heat at the time. And in fact, there were two competing notions, two competing ideas of what heat is. One of which is called the kinetic theory of heat. And it's still called the kinetic theory of heat, and that's the idea that heat is some sort of rapid internal tremor of the small particles of the heated bodies. Okay? So that's, if you will, a natural thought to have. If you start a fire, right, by means of sticks and fern, you rapidly rotate that stick and the friction generates a lot of heat. So it's sort of natural to have to make that connection between heat and motion. And in fact, today we know that this is ultimately what ended up being the correct picture. But back in the days, it was not obvious at all. In fact, here is a quote from these days where people speak about what science should or should not do. Science should relate observable quantities, but interpreting laws in terms of unobservable entities and are unverifiable fantasies. Okay, so to people, the crucial point here was small particles of the heated bodies, something they couldn't see, something that didn't have any other indications for its existence. And that was sort of that big step that prevented the kinetic theory of heat from being widely accepted, because it hinged upon the existence of some small constituent of matter that could, tremor and vibrate. And in fact, it had another big problem back in the days of Planck. If you think back to what he found, that mercury is a lot less efficient at storing heat than water is, but mercury is a lot heavier and so should contain a lot more particles. How does that go together? If I have a lot more particles, I should be able to store a lot more heat, but mercury doesn't, in fact, do that. Okay, that's indeed a paradox that was resolved a lot later, so that theory was really ahead of its time, but back in the days, people just didn't know what to make of it. Instead, what the consensus was at the time is that heat is a substance. That's called the material theory of heat. There is some matter that is heat, and that matter has a name, and it's called caloric. Okay, caloric is the substance that is heat. And so people wrote down a few aspects of the properties of caloric. First, caloric is an elastic fluid, the particles of which repel one another strongly. Second, the particles of caloric are attracted by the particles of ordinary matter. Okay, so that means that's the reason why your cup of coffee cools down. There is a lot of caloric inside the coffee, there is not so much caloric outside on the table, and because caloric particles repel and caloric particles sort of are attracted to ordinary matter around them, this is why the caloric leaks out of the pores of the coffee mug. And this is why the coffee cools down, because it loses caloric. People also thought, third, that caloric is indestructible and uncreatable. Okay, there's this magic substance, caloric. You cannot create more of it, you cannot destroy any of it, you can just move it around. And in fact, that also explained why objects, when they're heated up, expand, because more and more caloric flows into it, and so there needs to be some space to accommodate caloric, and that body would expand. And so it's natural to ask, okay, fine, if heat is some material quantity, does it have weight. Okay, so can I measure a weight increase if I heat up a piece of iron, say? Because all the caloric flows into it, why wouldn't that have weight? Okay, so if you put two equal metal spheres on a balance, one of which remains cold, the other one you heat up, if the balance is in fact horizontal at the beginning, both of those masses are equal, wouldn't the hot part of the metal gain weight and sort of tilt the balance that way? That was the idea, and in fact it turned out very difficult to really measure these things. You can imagine if you put a hot piece of metal there, you would get a lot of sort of air updraft that would immediately ruin your measurement and such. It was really, really difficult. And it became even more difficult once Black pointed out that there is more than one kind of heat. There is sensible heat and there is latent heat, and so there had to be sensible caloric and latent caloric. Started getting more difficult. But then that also provided a way out of that weighing iron conundrum, because people knew that if I melt ice, a lot of latent caloric flows into it, and so instead of weighing, hot, glowing hot metal and cold metal, which is very difficult, I could just weigh ice and water. Okay, if I put some ice cubes here and I put some water there, keeping the balance level, if then I let the ice melt, all the latent caloric flows into it, it should get heavier and the balance should tip. Okay, so the water that comes out as a result of melting that ice should be heavier than the water over there. But in fact, none of that happened. People did these experiments very, very precisely. They did not find that caloric had a weight. But instead of abandoning caloric, they went, okay, caloric doesn't have appreciable weight. Maybe it's just so light that I'd never be able to measure it. Today, this sounds a bit far-fetched and a bit ridiculous, but back in the days, this is what people thought. And they had, several good reasons to think that it's true, because you can make predictions with that theory. So that was the idea, and that was the time when we meet our next hero in France, a military engineer by the name of Sadi Carnot. Carnot was born into a very upper-class family in Paris, and he was educated at the most prestigious French universities at that time, which was École Polytechnique, that was put in place by Napoleon Bonaparte as a place to educate military engineers. And a lot of great French scientists were in fact educated there, and he would have them as his classmates. After finishing his university education, he joined the military as an engineer, and he would be posted to different locations in France. He would have to inspect fortifications and write a lot of reports that would then subsequently get ignored by his superiors, and he was very annoyed by that. He didn't really feel welcomed in the military. These were also very turbulent days. Napoleon had just been sent into exile, in fact came back in 1815, and his father briefly served as the war minister under Napoleon's sort of second reign. After Napoleon was toppled and the monarchy was put back in place, his father actually had to leave France. He was sent into exile. He was forced to leave. But he stayed in France. He stayed on the military. But he managed to be posted back to Paris as part of the newly formed general staff. Okay? And that meant that he could take leave on half pay, which he was very glad to do. He didn't like the work in the military. He wanted to go out. But he had to remain on call for duty. But with his free time that he would now have, he would show around. He would attend lectures at universities. He would visit factories because he was curious about steam engines. And he wanted to see how steam engines are used in practice and what people taught about steam engines at the universities. And so this is the time when we meet Carnot, 1819 to 1827, because in 1824 he writes a book about what he had concluded about steam engines. And that book, here's the very first page of it, it's written in French of course, but the title of it is His Reflections on the Motive Power of Heat and on Machines Fitted to Develop That Power. And the very first sentence that I put in red here goes as follows. This is, again, the context of his times. Heat possesses vast motive power no one can doubt in these days, when the steam engine is everywhere so well known. Right? Watt and Boulton, massive amount of steam engines, not just in England, also in the rest of the continent. This was really, the heyday of steam. The study of these engines is of the greatest interest, and their importance is enormous. Of course, he would go around, visit the factories. Everywhere he looked, he would find steam engines. But notwithstanding the work of all kinds done by steam engines, their theory is very little understood, and the attempts to improve them are still directed almost by chance. Okay, so clearly he just witnessed that enormous increase in efficiency over Watt and Boulton steam engine on top of Newcomen's. But to him, these are sort of almost accidental discoveries. Right? Watt had this great insight that to him was at the end of a long and arduous process of experimentation and measurement, and this is what Carnot acknowledges by that. So he says, given that dramatic 75% fuel efficiency improvement of Watt and Boulton over Newcomen, do the possible improvements in steam engines even have an assignable limit? Can I keep going forever? A limit which the nature of things will not allow to be surpassed by any means whatever. Okay? Was that 75% improvement already most of what there is still to be done, or is there an unlimited range of improvements that can happen in the future? And in fact, may these improvements possibly be carried out indefinitely? That's the question he wants to answer. For example, he says, are there agents preferable to the vapor of water for developing the motive power of heat? So he says, if I sort of take a step back, you guys have all been thinking about steam engines because water is convenient and abundant. But if I substitute water for something else, say alcohol or whatever substance you have, can I make an improvement in the efficiency of your engine? And in fact, it points out that the current establishment is not really well posed to answer these questions because the phenomenon of the production of motion by heat has not been considered from a sufficiently general point of view. He says all of the people working on steam engines are engineers, and they have very hands-on practical goals they want to achieve, and so they don't have the luxury of zooming out and thinking about steam engines from a sufficiently general point of view. But he has the luxury of doing that. He is on leave and on half pay, so he has lots of time, and he is very, very intelligent, so he does exactly that. And he says to zoom out and to not get lost, if you will, in the forest of steam engines, you should strip away all the practical details that we just went through in Watt and Boulton's case. And so to him, steam engines, or heat engines, in fact, is something like this, a big black box where heat goes in one way and motive power comes out the other way. And he says it's necessary to establish principles applicable not only to steam engines, but to all imaginable heat engines, whatever the working substance and whatever the method by which it is operated. Okay, so steam engines are fine, but they're just one instance of a much more general class of machines that I can possibly imagine building. And all of them are of that kind. But of course, he needs to draw some inspiration to know where to get started, and he turns to the Watt and Boulton steam engine, which is a natural place to get started. So he starts to think, what is the actual reason why this machine works? What is that makes it go? And he starts to follow the steam. And of course, these were the days of caloric, and so he says the machine starts by the steam, because the steam is what takes the caloric into the cylinder, right? The hot steam rushes into the cylinder, takes with it the caloric. And then the caloric inside the cylinder performs some function, it expands the cylinder. But then from there, the caloric, by way of the steam, gets pushed into the condenser. And then in the condenser, it's the cold water that is constantly springing there that takes possession of the caloric. Right? It condenses the steam, it absorbs the caloric the steam has had previously. And the origin of the caloric, of course, is the combustion of the fuel, the coal. Okay, that's the picture he has in mind. And so he says, it's not actually sufficient in a steam engine or any heat engine to have a heat source, a boiler that I heat with coal, that for him serves as a source of heat or as a source of caloric. You also need to have a cold part, okay, that can absorb the caloric at the end of the cycle. He says, the production of motive power is then due in steam engines not to an actual consumption of caloric, but due to its transportation from a warm body to a cold body. Okay, so here's the machine that puts out motive power. Caloric gets in one way, but the same amount of caloric, according to him, goes out the other direction. Okay, the caloric is transported from hot to cold, and as a result of that, the machine produces its action. And he reiterates, the production of heat alone is not sufficient, but it is necessary that there should also be cold, because without the cold, the heat would be useless. Now, is that obvious? Well, here's the argument that he gives. Imagine that you didn't have a body that was colder than your boiler. How would you condense the steam? If the atmosphere into which you want to eject the steam is as hot as the steam itself, the steam simply wouldn't leave the cylinder. And so after one stroke, your machine would stop still. It would not continue to function. That's why, in his world, and it's true, you need to have a hot body and a cold body, okay, which is not as obvious in the new common engine where everything happens in the same piston, but is a lot more obvious in Watt and Boulton's case where there's a hot cylinder and a cold condenser. So now he thinks, if we take that as a guiding principle, the fact that caloric needs to flow from hot to cold, how can I make that machine be as efficient as possible? Of course, I need to avoid losses to make it as efficient as possible, and so that means I should avoid hot bodies get in direct contact with cold bodies. Okay, the contact of bodies of different temperatures should be avoided as much as possible. Because if I do that, if I put a hot object and a cold object together, heat or caloric would directly flow between them and would not go through my steam engine. And because it would not go through my steam engine, I would not use that flow of caloric to produce motive power. Okay, so that's something that hurts me. I don't want to do that. Instead, he says, if I need to have a change of temperature, that should only occur by a change of volume and not by direct contact of hot and cold bodies. So what does he mean by that? Think about a piston or a cylinder that has some gas in it, which if you compress the cylinder, you push down on the piston, you would increase the temperature of the gas. That to him is admissible because there is no direct contact of hot and cold. Equally, if you pull out that piston, you would rarefy, you expand the gas, and then you would decrease its temperature. And that's also admissible according to him. Now these two things are very commonplace. If you pump up your bicycle wheel with a mechanical pump, the pump will get hot at the end because you repeatedly compress the air. You heat up the air. Equally, if you pop a champagne bottle, you will see a little mist appear, and that little mist is actually ice crystals that arise because of that expansion of the CO2 that was trapped inside the bottle that cooled down and produced ice crystals in the air. So both of these ideas, in fact, were known at the time, and this is what he set out to do. And then he continues and says, let me use these things as guiding principles and let me imagine what an ideal heat engine would look like. And he is very clear that he wants to design a heat engine purely on paper. Okay, a super idealized heat engine that could never be built in the real world, but that will nevertheless teach me something important about the nature of all possible heat engines. And he says, well, my heat engine needs to have a hot body and a cold body, as we just established. If I only have hot, nothing happens. If I only have cold, nothing happens. And I have a piston. And that piston has some working medium, which needn't necessarily be steam. It can be any medium, okay? But, he says, at any given moment in the operation of that machine, there will be a gas, and that gas will have a certain volume and will have a certain temperature. And as the piston moves up and down, the volume and the temperature are going to change. Okay? And he thinks about how that machine could operate. And in thinking about how the machine operates, he invents sort of a graphical way of representing what the machine does by showing the volume and the temperature of the working medium inside the cylinder. Okay? And he says the machine starts out by the cylinder being in the lowest possible position, the volume being the smallest possible amount that it will encounter as the machine operates, and the temperature being at the maximum. Okay? The maximum being the temperature of the hot body, the boiler that he has at his disposal. And he continues, now let's operate the machine. Let's couple that cylinder to the hot body so that caloric rushes into the cylinder, and let's expand the cylinder. Okay, let's move out the piston. But he says, wait a second, if I move out that piston too rapidly, the gas inside will cool down and it will fall below the temperature of my hot body. But then I have exactly what I didn't want, namely a hot body and a cold body in direct contact. So I need to be very, very slow in moving out the cylinder so as not to make the temperatures be different, but to ensure that the temperatures stay the same all the time. Okay? So he moves across. The temperature stays the same. There's never any difference in the temperature, but the volume goes up. And then at a certain moment he says, now it's enough. Let's insulate the piston again. Let's move it away from the hot body. But let's continue to expand the gas inside. And of course what happens then is the volume continues to increase as it pulls out the piston, but the temperature now goes down. There's no more caloric flowing into it. And now he has tuned things exactly such that once the piston reaches the top end of the cylinder, the temperature inside has cooled down to be exactly the same as the temperature of the cold side of his machine. And the reason why that's important is because now he can put his cylinder in contact with the cold side of the machine, And again, there is no difference in the temperature. Everything is at the same cold temperature. And he can start to push the piston back in. And again, he has to do it very, very slowly, because if he does it too rapidly, the temperature would heat up too quickly, and again, you would have losses. So he does it very, very slowly, up until a certain point, when then he decouples it again, but continues to push in, such that the gas inside, not having anywhere to leave its heat, heats up again. Okay, and it heats up exactly to where you started from, so you have a repeating cycle that machine could go through over and over and over again. In fact, he points out that you not only have to do it slowly, you have to do it infinitely slowly. Okay, even a single revolution of that machine would take an infinite amount of time. And that tells you that you can never have such a thing operate in the real world, but there's a nice illustrative thing that you can do on paper, and we'll see in a second why it's important. But you see, he says that this makes apparent what the function of that piston is. It's like a syringe that sort of, absorbs caloric. I sort of extend the piston, I take up the caloric, I move it across to the cold side, and I use that syringe to push the caloric back out into the cold side. Okay, that's exactly what the steam engine is doing. It's taking caloric in, pushing caloric out the other end, and producing some motion by the cylinder moving up and down as a result. And he claims that something like this infinitely slowly operating engine, is the most efficient heat engine of any kind. And he, in fact, gives a proof as to why that's the case, and we'll see the proof in a second. But before, he notices one more thing, that in this circular fashion in which the machine operates, I go clockwise, but I might as well go counterclockwise. Nothing stops me from going through my operation in the opposite direction. I could start at the cold side, expand the piston while keeping the temperature the same, decouple the piston, push it back down so it gets hot, and then couple it with the hot side, push it all the way down, decouple it again, pull it up again so I get cold. Now I have a heat pump. I will syringe up caloric from the cold side and push it back out the hot side. I have something that can cool down a cold body and convert that caloric into a hot temperature, which it then can radiate away on the hot side. This is how your fridge works. It continuously pumps out heat from the inside to the outside of your kitchen. Okay, the outside is much hotter than the inside. So he has both. With a single stroke, he invented the most efficient heat engine, but he also invented the most efficient fridge, if you want. And now here is this great idea, and that to me is one of the most magical ideas in all of physics, in all of eternity probably. And it's the proof as to why his steam engine, his heat engine, is in fact the most efficient one that you can imagine. So here's how the proof goes. He says, in my steam engine, in my heat engine, I have a hot side and a cold side. And I can run my engine that I can only build on paper and never in the real world, I can run them between the two things. Okay, it will take up caloric from hot, the caloric will flow through the machine and will be expelled on the cold side. And in doing so, the machine would give me a certain amount of motive power, okay, that I can use to run a factory or do whatever with. And he says, let me put in that, say, between that same two hot and cold bodies, let me put one of my heat pumps. Let me put the mirror image of my heat engine, and let me use the motive power that my heat engine generates to drive the heat pump. Okay, let me not take it to run a factory, let me use it to drive a heat pump. So you see what happens. That engine has caloric flowing from hot to cold, and because that's the exact mirror image, it would pump back up the same amount of caloric from cold to hot. Okay? So the machines set up in this way would work indefinitely because they would just have the caloric cycle between hot and cold. The engine would allow the caloric to fall from hot to cold, and the pump would pump it back up, much like water. Okay, this is something you can imagine. In fact, if you put this into a box, you wouldn't notice from the outside what's happening. Right? The caloric is flowing in a circle, but likewise there is no motive power that's sort of useful, no excess motive power, because the entire output of the engine is used to drive the pump. Right? There's nothing useful this thing can do. But he says, hang on a second, what if there was something that was better than my engine, something that was more efficient than my claimed most efficient heat engine? What if I put that into here? What does it mean to be more efficient? Well, it means for the same amount of caloric that flows from hot to cold, I can do more than just driving the heat pump. I have some excess power available that I didn't have before because now I have a more efficient heat engine. Okay, but you see what happens. Still, the caloric is flowing in cycles, but now, because I have this better than my supposedly maximally efficient engine, I have some additional power that I can use for something. So that arrangement, if it could really be built, would produce motive power out of nothing. Right? If I put this into a box, caloric goes in cycles between hot and cold. I never get to see that from the outside. What I do get to see from the outside is that excess power that comes out. Out of my black box, I can power whatever. Okay? So somewhere in my thought process, I must have gone wrong, because this can clearly not happen in the real world. And he says, well, yes, you have gone wrong, and the fact that you have gone wrong is that there is nothing that can be more efficient than my heat engine. So by supposing you could replace my heat engine with your apparently much more sophisticated one, this is where you went wrong. There can be nothing that is more efficient than my engine. Okay, and you see, this applies to a heat engine of any kind, irrespective of how it's built and how it works. There cannot be a heat engine of any kind that's more efficient than this simple syringe-like piston moving back and forth.
Yes, what's bothering me is if this piston is moving infinitely slow, it's not doing any work. And if it's not doing any work, it's not an engine.
Can we discuss this afterwards? There's an answer to that. Very good. Hold your question, please. So Carnot says, at most what I can do is to pump caloric in circles and not get any excess power. Okay? So imagine that I had maxed out my efficiency by using my engine of a certain type. What if somebody came around and used that same engine but with a different medium? Could that maybe be more efficient? And he says, no, it cannot, because if it were, that same paradox would immediately arise again. Okay? So that means, irrespective of what the substance is that the heat engine works with, it cannot be more efficient than another substance. So I can build a steam engine, I can also build an alcohol vapor engine, but the maximum efficiencies of both of them would be exactly the same. And likewise, I can have a very sophisticated internal construction. I can have several pistons, I can have them all kinds of things. Again, there was no increase in the maximum efficiency that you can achieve by any means of engineering whatsoever. That's what he concludes. So any Carnot engine is as good as any other Carnot engine. Okay, that's a very, very profound statement. The maximum possible efficiency of any heat engine cannot depend on how that heat engine is built. It can only depend on how hot the hot side is and how cold the cold side is, because that's the only thing that you can affect. And that's what he concludes. So at the end of his book, he makes a list of how to build a good heat engine. You need to make the hot side as hot as you possibly can. You make the cold side as cold as you possibly can, so you have a large fall of caloric. And you need to avoid to bring hot bodies in direct physical contact with cold bodies, because that will give you losses, and losses are not allowed if I want to be very efficient. As we said, such a machine would be very, very slow and would not work in the real world. But what to me is the most important of his conclusions is that there is many things that do not actually matter. Namely, the operating medium of the machine. I don't need to waste my time running through all the possible substances I can imagine to test them out in the real world, because I know, ultimately, they will not gain me anything. Likewise, I don't need to lose myself into doing very elaborate technical constructions in my machine. Ultimately, those will not make it substantially more efficient than any other equally developed heat engine. So this is an example of where, once you understand the fundamentals that governs your machine, you immediately understand what is possible or what is impossible. And that's very important in sort of directing engineering into the right channels and not allowing people to sort of waste their time optimizing things that don't matter ultimately. But he also puts a disclaimer at the end of the book, where he says, these conclusions are based upon the theory of heat as it is understood today, and it should be said that these foundations do not appear to be of unquestionable solidity. Okay, so he works in terms of caloric, and if you go through his notes, you will see that he already has doubts as to whether caloric is really real, or whether heat is something entirely different. And in fact, Carnot died very, very early as a result of a cholera epidemic. He was only 36 when he passed away. Had he lived on for longer, the caloric theory might have died a lot earlier than it eventually did. So let's see how the caloric theory died. And a person who set out to, in fact, kill the caloric theory was Benjamin Thompson. Later on in his life, Count Rumford. He was a real jack of all trades. He fought on the side of the British in the American Independence War, where he did experiments as to the explosive power of gunpowder. then he went to London, having sort of the aura of a scientist, because he did all of these experiments with gunpowder behind the front lines. Eventually, he came to Munich, and this is where he did everything that you can imagine. He designed military uniforms for the Munich army. He invented soup recipes to feed the poor in Munich, very nutritious but very easy to make and cheap soups. He also planted a lot of trees in one of the largest public parks in Munich, the English Garden. He was just very good at many things. And he lets us in as to what his secret, if you will, is, which is the following. He is persuaded that a habit of keeping the eyes open to everything that is going on in the ordinary course of the business of life has often led to useful doubts and sensible schemes for investigation and improvement than all the more intense meditations of philosophers in the hour expressly set apart for study. So he's somebody who goes through life with his eyes wide open, looking for opportunities in every corner. And this is how he managed to do all of those things. And this is how he managed to do the following experiment that I'm about to explain. It's called today the cannon boring experiment. And as he says, again, it was by accident that he was led to make the experiment of which he is about to give a report. Remember, he was a military person, so at some point he was engaged, lately, in superintending the boring of cannon in the workshops of the military arsenal at Munich. I was struck with the very considerable degree of heat that a brass gun acquires in a short time in being bored. Okay, so that means you take a solid cylinder of metal, the gun barrel, the cannon barrel, and then you have a borer, you mount it such that it can turn along its axis, and you have a borer that sort of hollows it out, so you get a gun barrel. It's like what you would today have in a lathe. So there would be a shaft that would be powered by horses going around in circles that would make the cannon rotate, and that borer would be fixed and would then, over the course of many hours, hollow out the cannon. And in the process of this boring mechanism, he noticed that the gun gets very, very hot. And so then he says, a thorough investigation seemed to give a further insight into the hidden nature of heat. Okay, he has his eyes wide open. He says, there is some sort of source of heat here. Maybe I can learn something from that. And so he goes on to design an experiment. In fact, he was very careful in pointing out in his report that his experiment that he did on a real cannon was constructed in such a way as not to prevent that cannon being useful afterwards for his real purpose. Okay, he was very careful not to take any resources away from the military, in any cannons in particular. And so he did his experiments with that little cylinder of metal that was attached at the end of the gun barrel. Okay, so that would eventually not be used, and it would be scrap metal anyways, and that's what he used. So there's this metal cylinder, okay, and he already had hollowed it out part of the way with a real borer, but then he puts in a blunt borer, okay, something that doesn't really cut metal, but just pushes against it. A very hard piece of metal, but doesn't cut. And then he had his horses go and sort of turn that entire shaft all the time, and that borer would be pushing against the inside of that metal cylinder, and it would generate a lot of friction. Okay, so so that metal cylinder would get very hot. And so he used this friction deliberately as a source of generating large amounts of heat. And then he builds a wooden enclosure around that metal cylinder made out of wood, and he fills it with water. Okay, such that the entire metal cylinder, which gets very hot, is immersed in water. Okay, and then he begins his report. The box was filled with cold water of temperature of 60 degrees Fahrenheit, and the machinery was put into motion, with the cylinder rotating at the rate of about 32 times in a minute. Okay, that's what the horses could manage. And then he puts a thermometer into the water. He says, at the end of 1 hour I found, by plunging a thermometer into the water of the box, that the temperature had now been raised to no less than 107 degrees Fahrenheit. At the end of 2 hours, the temperature of the water was found to be 178 degrees Fahrenheit. At 2 hours and 20 minutes, it was 200 degrees Fahrenheit. And at 2.5 hours, it actually boiled. This is his capitalization, by the way. He writes it like this in the report. He was clearly very struck by the fact that he could make water boil simply by having horses go around in circles and driving his blunt borer and pressing it against the metal. So then he asks his question, where did this heat come from? The caloric theory was still widespread, so he tries to think, what would a caloricist answer to that question? Where did that heat come from? In other words, if that metal cylinder was very hot, a lot of caloric must have flowed into it to make it so hot. So where did that caloric come from? What is the path it took to get inside the cylinder. And he goes through a long list of possible sources. Was it furnished, for example, by the small particles of metal detached from the larger solid mass and they're being rubbed together? Okay, what he has in mind here is the metal chips. Even if you have a blunt borer that doesn't cut effortlessly, it will still grind down some of the metal over the course of multiple hours. You get some very fine-grained metal dust inside. Is it that metal dust that in the process of being made to dust, that liberates the caloric? If this were the case, he says, according to the modern doctrine of caloric, the specific heat of the metal chips ought not only to be changed, but the change undergone by them should be sufficiently large to account for all the heat produced. Now that's a very long sentence, and I had a lot of trouble understanding exactly what he means, but this is what I think he means. So he says, if I start with my solid metal at the beginning, and I put it through this process of being slowly ground down by my very blunt borer, at the end I end up with metal chips, and a lot of heat, a lot of caloric that somehow must have come out of that process as a result. So he thinks that this caloric has actually been squeezed out of the metal in the process of the metal being ground down to chips. The caloric was in the metal from the beginning, but by turning the metal into small chips, it somehow liberate the caloric. But he says this is only possible if afterwards the properties of the metal chips are different from the properties of the metal that I had at the beginning. In particular, if the caloric comes out of the metal, it must be so because now the attractive forces between the caloric and the metal chips is less than the attractive force between the caloric and the original solid metal. Otherwise, the caloric would have stayed inside the chips. It would not have come out. But it also means, if that is less attractive force, the chips would now be less likely to absorb caloric when I heat them back up. So the specific capacity of heat would be different between the metal chips and the solid metal. So he collects all of his metal chips and he measures the capacity of heat, but he says no change had taken place. He says these metal chips, for all practical purposes, behave exactly like the original solid metal that he had. So this, according to him, cannot be the source of the caloric. Where else could the caloric have come from? Could it have been furnished by the water that surrounded the machinery? He says that's ridiculous. The water absorbs all of the caloric. That's why it gets hot. It cannot be a source of caloric. Likewise, was it maybe furnished by the metal that surrounds it? He says that's equally ridiculous. The metal also gets hot. It cannot possibly be a source of caloric. And so he concludes that the only way in which there is heat generated out of nothing is in the following. He says, it's very difficult for me to form any distinct idea of anything capable of being excited and communicated in the manner in which heat was excited and communicated in this experiment, except that heat is motion. He says, this experiment that I've just done is absolutely incompatible with the idea of there being some external matter, namely caloric, rushing into my metal and into my water. There is no possible way this could have happened. Heat must have been generated in a different way, namely heat cannot be caloric because I have no way of making that work. That's what he did in 1798, but unfortunately the caloricists did not really accept his conclusions. They pointed at too many loopholes in his experiment. Maybe he even blew his own horn a bit too much in communicating the experiment, as we had said. But it's true, there are some real downsides to how he conducted this experiment. Because he used horses, he didn't really have a very good handle on controlling the amount of mechanical energy that he used to make his experiment. Likewise, the exact amount of heat that he generated was also not very well controlled. He put a wooden box, he put some thermometers sometimes at different intervals, but he didn't make any attempt whatsoever to catch the entirety of the heat that is produced. And that's why, people did not accept his conclusions, which was to totally upturn the dominant view of science at the time. He makes a bold claim. There was another person, 50 years later, who set out to remedy his shortcomings, and that person was James Joule. He was again from England, and he was a brewer, or his father was a brewer, which, when his health deteriorated, James took over. And brewing beer requires a very precise control of temperatures over very prolonged periods of time. So as he grew up, he had a lot of exposure to measuring temperature, and he got a real intuitive sense for what it means to have control over temperature. He was also a very keen scientist. He played with many things, and these were also the times when electricity was very modern, and he started building some small electric motors beside running his father's brewery. And so, eventually, he set out to repeating Rumford's cannon boring experiments in a different way, in a much more precise and controlled way. He replaced the horses by the following scheme. He has weights that he would suspend from these rods, that he would then have wound around this wooden post here, and as the weights move down, they would simply turn that shaft. Okay, so he replaces the horses, which are not very well controlled, by two weights, which you can weigh very, very precisely, and he can let them drop down by a very, very precise distance, which you can also measure by a ruler. So he fixes one of Count Rumford's shortcomings. He also fixes the other one by connecting that shaft to what he calls a friction chamber, okay, a solid metal box that's very well insulated, so no heat can come out. It's not at all like Rumford's wooden box. It's a real metal cylinder with a lot of insulation. And inside that friction chamber, he puts a paddle wheel. Okay, this is seen from the top. There's just a paddle wheel that would be turned by your threads being pulled down by the weights. And so it would try to spin around the water that he would fill the friction chamber with. But he doesn't want to spin around the water, he wants to generate friction. And so he wants to block the flow of the water as much as possible. So also he had some fixed fins that block the flow of the water, and so there would be a lot of turbulence and there would be a lot of friction. So mechanically it would actually be really, really difficult to turn, if you will, the crank here with your hands. And then he sets up this experiment, and he drops down the weights, and he measures very, very carefully, and he gives us all the data that he had gathered. Okay, you can see he measures the distance by which he drops down his weights to 1/100th of an inch with his ruler, and he measures the increase in the temperature that this resulted in inside the water of his friction chamber to 1,000th of a degree Fahrenheit. Okay, so you really need precise thermometers, and this experiment could not have done until there were precise thermometers available to him. And then he says, well, now I can compare the two. I can compare by how much I've dropped my weights, I can compare by how much I've heated up my water, both of which I have extremely, extremely precise measurements of. And he says, increasing the temperature of a pound of water by 1 degree Fahrenheit requires the expenditure of a mechanical force represented by the fall of 772 pounds through the space of 1 foot. Okay, he says, if I put up 72 pounds and I let them drop by 1 foot, and direct that mechanical energy through my threads and my paddle wheels into the water, if I put 1 pound of water inside, I would get exactly an increase in its temperature by 1 degree Fahrenheit. And in fact, he repeated this experiment, or many other experiments, to show that it doesn't really matter how you generate mechanical energy and how you direct that mechanical energy into the water. It doesn't matter at all. You can do it with the paddle wheels, as we just said. You can also do it by simply pushing the water through tiny holes, like in a sieve. There's the water sort of frictioning with the walls of that sieve that would also raise the temperature of the water. Here's a sketch from his notebooks. You could even, he says, because electricity is a thing now, you could even do what we said in the first lecture. You could use that crank to spin a magnet to generate electricity, then use that electricity to heat up the water. Again, I need to turn the crank by as much as it takes to raise, he gets a slightly different number, to raise 896 pounds to the perpendicular height of 1 foot. Okay, so all of those experiments give slightly different numbers, but that's because there's always some experimental error. But he concludes, all of those numbers are always in the same ballpark. It simply doesn't matter how I generate the heat. It's always roughly the same. And in 1849, 50 years after Rumford, he concludes that heat can simply not be a substance. Irrespective of how I generate heat, I can, through whatever sophisticated scheme I can make up, it's always exactly that same quantity. It's simply a mechanical effort. In fact, he phrases it as an equivalence between heat that goes into water to raise its temperature and a certain expenditure of mechanical effort. The two are simply equivalent. Heat is not a substance, but heat is a different form of energy. And the rest, as they say, is history. A few years later, Clausius followed up, and he says heat is actually more than just a mechanical effort. It's the precise average kinetic energy of the molecules inside my water. Later on, James Maxwell, who we'll meet again, he calculates even more precisely. He now says that there's not just the average kinetic energy, but there is more to that, and he can point out exactly what happens. People built on top of that knowledge, they built the first steam turbines.
heat became more and more useful. And then later on, 1892, Rudolf Diesel in Germany, he built the first diesel engine. And in fact, he let himself be inspired by the theory that Carnot put out. He knew exactly what he had to go after to make his engine as efficient as possible, because Carnot laid out a plan to do so, and the diesel engine was the result of that. And so today, we have these wonderful large steam turbines that still produce a vast majority of our electricity, and we have internal combustion engines, diesel motors and other ones, that also are just the continuation of what Carnot started. So now we've seen what the nature of heat is and what it eventually led up to, a lot of the things we have today, but we opened a new question, because part of why James Joule's experiment was so convincing is that he showed even if I take the detour through electricity, and I don't simply produce friction, but I first produce electricity and then produce heat, I still get the same answer. That is a lot of what convinced people eventually that heat is universal, and so now we need to explore what the nature of electricity is. But that will then be for next time. Thanks a lot. Okay, so let me answer your question first, if I may. If it's still a question, on the Carnot engine being very, very slow.
Oh, yeah, the idea of the cycle that moves infinitely, and yeah, how can you call that an engine, representative of an engine, if there's no work done?
But so once it has completed a cycle, there will be some work that has been done. You just need to wait until the cycle is complete. Okay, if you imagine a real steam engine that takes about a second to run through its cycle, and you record a movie of that and you slow it down, at the end of the movie, the exact same thing will have happened. It will have just taken longer. Okay, so that's the idea. You just have to wait for longer, but there is nothing that sort of you would lose by having to wait longer. In fact, it gets more efficient as you need to wait longer. Does that make sense? Okay. Any other questions? Yes?
Thank you. This is a terrific talk. And just as an aside, that for Carnot, the expansion, like a Joule Thomson expansion, his example was champagne.
Right.
That's terrific. I'm going to use that at parties.
Thank you.
Going back to Black and to Watt, you had said that in the caloric theory, they thought there'd be two different substances, a sensible caloric and a latent caloric, if I understood you properly.
That's right.
And I don't think I follow why they would conclude that. Why would they say it has to be two different substances?
So there was latent heat and there was sensible heat. And the two had very different effects. If you put sensible heat into something, the temperature rises. If you put latent heat into something, the temperature doesn't rise. But instead, water turns into steam and such. Okay, so they thought, and they didn't have a microscopic explanation at that time. I mean, the whole point why the caloric theory was still accepted was that people didn't believe in the notion of there being atoms and molecules and such. So when you think about this, you need to sort of think from a weird perspective where there is no underlying mechanism for these things. All you know is that in different circumstances, there is different kinds of heat because they do very different things. One raises the temperature, one doesn't raise the temperature. Right? So now if you invent a concept that is a stand-in for what I now call heat, I mean, I use the modern version of heat. Back in the days, people called it caloric. And so if heat is a substance that if I inject it into a body makes it raise its temperature, or if I inject that substance into a body and it makes it go from water into steam, these are different substances. They have different effects. And in fact, there was a time when there was a weird sort of intermediate notion that sort of sat between the caloric theory and the kinetic theory, where people started thinking about, well, if there's different kinds of caloric, how are they different? Right? So what are they made of? And sort of how do they interact with the body into which I inject them in different ways? And so at some point, there was this weird hybrid theory where people already started thinking that there is atoms or molecules, and they imagined them as spheres and such. And sensible caloric, they imagined, would sort of go into the spheres and make them expand. Okay, sensible caloric raising the temperature, expanding the object. It would have to go into the spheres and increase somehow the radius so the entire body expands. But then latent caloric wouldn't do that. It wouldn't expand the body. It would, in fact, they thought, form sort of a thin atmosphere on top, outside of that sphere, Okay, outside of the atoms, it would sort of condense on the surface of these atoms, and therefore change the way the body appeared. These atoms were sort of, stuck one next to the other in a solid, like in water. But then once they had acquired these atmospheres of latent caloric, they would now be different. And that's why the water turned into steam and such. Okay, that was before they finally accepted what the real world is like, namely that there is no such atmosphere and there is no such caloric, it does one thing or another. People just tried to make up some explanations for how to fit the facts they observed. Sorry, did you have another question?
I mean, I don't really want to argue the point because obviously there's so many problems with it. But I would have thought Watt would have done some experiment. He's condensing steam. Wouldn't he measure the temperature increase of the water?
Yes.
So one is there's the latent heat from condensing the steam, and then he's turning it into
right.
What would seem like sensible.
That's right. That's right.
And I would have thought they would have concluded at that moment it's the same thing, but they didn't.
Right. I mean, wonderful point. I mean, you have this reasoning because you sit outside of that paradigm. If you sit inside of that paradigm, you try to go to very great lengths to preserve that paradigm. Right? I mean, even here, when people sort of did all of these weighing experiments, okay, 1 second. When people did all of these weighing experiments, and I couldn't find that if I melted ice, the weight would increase, irrespective of how sophisticated I did my experiments, you might have also concluded, well, caloric simply doesn't exist. Right? Instead, they concluded, well, it just doesn't have any weight, and therefore make it even harder and harder to pin it down. Right? In fact, that's the way that many scientific theories went. At the beginning, you can write them down in a few lines of axioms, if you will, or assumptions, but then as more and more facts accumulate, you have to make the assumptions and axioms more and more elaborate, and you have to bend over backwards to make the theory still work. Right? And this was one example of that, until eventually it becomes so great of a discrepancy that you cannot possibly uphold it anymore, and then it breaks. Okay, but before it breaks, you do everything you can to stay within that paradigm, and I think that's one of those cases.
Could you discuss why when water goes to ice, the volume of ice it expands, and you have an enclosed space, you break the pipe?
Say again? Why the volume of water
When you have water in a pipe, you
Yeah.
freeze it, it expands,
Right.
and if the valves are closed, the pipe breaks.
That's right.
So there's that expansion. You talked about expansion of the steam end, but
That's
not
right.
between liquid to solid.
Right, very good. So the question is, if I have water and I freeze it, the ice occupies a larger volume than the original water did, and that's why sometimes pipes break and such in the winter. And the answer is that, okay, from today's perspective, we know what water is made of. It's made of water molecules that are sort of arranged in very random ways in liquid water, because I can effortlessly shuffle them around and such. If I cool it down, the water will crystallize. It will form an ice crystal. So when liquid water is liquid, all of the molecules, they shuffle around because there is a lot of temperature and a lot of heat. That's why they do not sort of form stable bonds with one another. If I cool down the water sufficiently much to get rid of all of those vibrations, which we know today heat is, eventually those ice crystals, the ice molecules, will start to arrange themselves in a more regular fashion than they are in real water, and that just takes more space. And that's why the volume is larger at the end.
And a quick question on the patent workaround. During that time, what was the duration?
Sorry, which patent?
When Watt was
Right.
and his partners were
Right.
working around the crank mechanism
That's right.
with their gears,
Yeah.
how long did they have to wait to get that patent to expire?
So the question is, they worked around the crank with this very elaborate scheme that wasn't really useful for anything other than avoiding having to pay patent license fees. And eventually they abandoned it as early as they could for sake of the crank, which is a lot simpler. There was a very weird period where Bolton, Watt's business partner, actually lobbied the Parliament of Britain to keep Watt's patent upheld, but to let expire that patent. Okay? So, they did everything they could. I mean, Watt himself wouldn't have done it. I mean, you saw what his sort of, business practices were. But Bolton, he was a real industrialist and a businessman, so he knew he could pull it off, so to speak. So they tried everything they could to get an advantage out of that. And I don't remember the exact period of years. It must have been, I think, of the order of 10 or 15 years. So it wasn't immediate that it expired. They built many, many engines. In fact, most of the ones that still survive from these times, they still have the cogwheel gear, the planet and sun gear. Yeah. Any other question? Yes.
Make a comment. I think it was Einstein who finally put the final nail in the coffin.
Very good.
With his paper on the theory of the Browning motion.
That's right.
And that nailed it down. That people then had to believe in molecules, and they didn't. A lot of them didn't.
So-
But Boltzmann had a problem with that.
So there is a,
It was suicide.
right. So the comment is that, okay, if you go back to Joule, well, he made a very convincing case, but he didn't make sort of a conclusive case because he sort of quoted all of this evidence that irrespective of what you did, in the end you just ended up with the same amount of heat. But if you conclude that there is really motion of something and this is a mechanical effect, then why can't you see the motion? If I look at this table, why don't I see the table sort of vibrating and jiggling around? And so the comment that was made is that a lot later, people did actually see the motion. They took water, a small water droplet that had some pollen grains in it or some small like dust particles, and they put it under a microscope. And in a warm lab environment, all of the water molecules would jiggle around. And then you would see, if you looked through that microscope, you would see the pollen grain or the dust particle, which is a lot larger than the water molecules. It would permanently get hit by the water molecules, and it would sort of move in very, very random ways because it would all the time be bombarded by water molecules from all directions. And so if you look through that microscope and you trace the path of that pollen grain, it would seem like a very random trajectory. And that's what people then call the Brownian motion. Okay, as today has become a synonym for like very random seeming motions. And that ultimately showed them that in fact things do vibrate because if I put a small enough object in, it will feel those vibrations that I can look at them. But that was a lot later. And thanks a lot. Okay, back there. Yes.
I would assume that in the process of trying to preserve a paradigm, situations would arise that challenged it, but because of the urgency or the priority of preserving the paradigm, those things were discarded. And it took an effort, a battle, or whatever, to finally cause a breakthrough, to go from one paradigm to another paradigm. It's like the latent energy changing the state, from a solid to liquid or whatever.
Yes. Wonderful comment. In fact, so the comment was that in the process of a paradigm being overturned and being replaced by something else, there can be a period before that transition happens where there is a lot of experimental evidence that if looked at in the right way, it's plain to everybody to see that the current paradigm is in fact false. But because people think and work and operate in the old paradigm, they choose not to look at the experimental evidence in that way, or it's not apparent to them to look at the experimental evidence in that way. And that's how that transition is sort of delayed to a new paradigm. In fact, we're going to see a very good example of that later on with the fission of uranium. It turns out Enrico Fermi split the uranium atom in Rome way before the German team did it later on in Berlin, which today are credited with the discovery of uranium fission. So Fermi saw all the evidence. He did not interpret the evidence in the right way because he was not simply prepared to accept the fact that uranium could be split. And later on he called this a massive blunder, and he would always be very, very frustrated when people remind him of that oversight of his. But so you see, nobody is immune to that sort of aspect of things. Yes?
In air conditioning technology, they use the latent heat and the sensible heat.
Right.
How do they determine that? That's one question. And they have developed a quantity called tons of refrigeration, tons of heat. How do they get from latent heat to that ton?
Very good. So there's two questions here, actually. The first question is, if you go back to that fridge of Carnot's, you see, I made it sound very simple. I said there's simply some gas or some operating medium that the engine works. And I didn't tell you this, but I sort of assumed in telling the story that that gas, as you expand and compress it, would always remain a gas. It would never turn into a liquid. Okay? But today, in fact, if you open up a fridge or an air conditioning unit, you would actually find a medium inside, which is deliberately chosen such that it would turn from a gas into a liquid as the piston is pushed down, and back from a liquid into a gas as the piston is expanded. And that's precisely to make use of that additional heat capacity that you get for free, if you will, if you boil it from a liquid into a gas. Think back to what James Watt has found in the opposite direction, that you couldn't get with a working medium that stayed a gas all the time. Okay, that's sort of an engineering trick that people have found, and that is in every fridge and every air conditioning unit today. Could you remind me of the second question, please? Oh, right, so very good. So the first unit, in fact, was a BTU, British Thermal Unit, that, in fact, already Joseph Black, implicitly had when he invented his concept of capacity for the measure of heat. A British thermal unit is a measure of heat. And if you take a pound of water and you put a British thermal unit, a BTU of heat, into the water, you would raise its temperature by 1 degree. Okay, that's what it means for 1 BTU of heat. Now, if you have an air conditioning unit that has a certain amount of BTUs in its data sheet, that would simply mean that it could transport that much of heat from your room out into the sort of warm environment within a certain time. And then, okay, this is the unit even today some people use, and then obviously there's other ones that you can all convert if you know the appropriate factors, which I don't.
So that's amount of heat to cause to freeze a ton of water. Is that the idea?
I don't know exactly what 1 ton of heat means. I'm not familiar with that. There's some conversion factor. Units are all the same. Yes?
Expanding on the gentleman's question or comment about the shifting paradigms, what I want to know is what was the understanding of the nature of matter during that century? Because I thought that the atomic nature of matter sort of came later.
Right.
So what would, in terms of this idea of fluidity and what was the understanding of matter from the mid-1700s to the early 1800s?
Very good. People did, in fact, have some vague notion that matter is made of small objects. They didn't have a clear name, or if they did have a name, they wouldn't know exactly what they meant by that name. That was one sort of illustration how somebody noticed that there's something to do with small quantities of matter and such, which is in a church. If you sort of blow out a candle at the front end of the church, even at the back end of the church, you could feel the smoke of sort of the candle being blown out a lot quicker than it would take the air to really traverse that distance. Okay, so that was already some indication that the smoke was made of small particles that again sort of diffused through the air a lot faster, because of that of that Brownian motion kind of thing, than it would really take to physically move that chunk of smoke back down. So there were anecdotal evidence, let's call it, for matter being composed of small bodies. The actual idea dates back all the way to the Greeks, and we're going to see that part of the story afterwards. But the first real sort of tangible facts came from chemistry. That people noticed that if you put 2 amounts of hydrogen and 1 amount of oxygen together, you would get water and nothing else. So that told them that there is some whole number ratio with which you need to combine different substances to form another substance without leaving any residue. That would then point to somehow the discreteness of the composition of different classes of bodies.
About what date was that?
That was late 1700s.
Okay, so what I'm getting at is, was there something in science that was discovered that was necessary before people developed the kinetic theory of heat?
You mean a concept that needed to be discovered?
Well, yeah, in terms of the nature of matter. Such that the kinetic theory probably couldn't have happened before the date it did.
I don't know for sure. I think the answer is no, because the whole reason why it took so long for the kinetic theory to take hold, and even for the caloric theory to be very successful, is because ultimately the way heat behaves in most circumstances doesn't really depend so much on how matter is really made of. I mean, Carnot's theory was purely based on caloric. It still holds true almost exactly to this date. You only needed to change it ever so slightly by recognizing that in fact there is no caloric and in fact there is motion as the origin of heat. And likewise, the kinetic theory, you could get almost all the way without having a very precise understanding of what the nature of those molecules is that you are really vibrating. As long as you are prepared to accept that there is something that vibrates, you're almost good to go. Modulo, small little sort of things, like what I mentioned here, that people were confused about the capacity of heat in mercury versus water. Right? If both are made of molecules, mercury is made of molecules and water is made of molecules, how come, and assuming that the kinetic theory is true, how come that mercury is so much less efficient in storing heat than water is if both of them are just vibrating bodies, right? At this point, indeed, the structure of the molecules becomes important. And these aspects tended to be resolved a lot later. Okay, but people were prepared to accept a different paradigm, even in some cases, before all of the small little questions were resolved. Okay, at some point, the body of evidence simply becomes too great to totally ignore it, and you can apply it to solve most problems if you're prepared to sort of are positive that later on and optimistic that later on you can resolve even the fine open questions still. You don't need to know exactly what the matter is made of. Does that make sense? Yeah. Okay. There was yes, please.
Yeah. Since we're talking about this particular theory and caloric, maybe particles, did anyone make the connection of like light, which is pure energy that we know now, that the particulate nature of light might lead to a general theory, not just heat, but well, heat, you got heat from light anyway. It's sunlight.
Right.
So did anyone make that connection or was thinking about that at that time?
Not until much later, as far as I know.
Not until
Yes.
late
It was
1800s?
Yes, late 1800s and early 1900s. This is when light was everywhere, and people looked at light in all different kinds of ways. But for a very long time, light was simply a light ray. Eventually, it became a wave, and eventually, it became a particle, or it became both, really.
Did Newton entertain the concept that light could be made of particles?
So there.
Somebody did.
So there was this discrepancy, right? There was Newton and there was Huygens on the continent, right? And they had different notions. Huygens thought it was a wave. Newton thought it was this corpuscles or whatever he called them, like small little particles of light. Say again.
Faraday invented the field concept.
Faraday invented the field concept. That's right, but he didn't yet make the connection with light. That Maxwell did that after Faraday sort of laid the ground. So there was a time when there were many confusing, just as with heat. At the beginning, there is utter confusion, then there is quantified utter confusion, and eventually there is sort of a breakthrough and people understood things fall into place, right? It was similar with light and particles and such. Okay, there's one more question.
Do we know when the term atom or molecule was first used? Stabbing in the dark as to the smaller particles in a substance like the desk there.
So, right.
We need to have some terminology
Right.
for what little particles might be.
Very good. So the question is, when people started to entertain the notion of atoms, or when they started using the word atoms to mean something, and I can point you to the 6th and 7th and maybe the 8th lecture where we'll talk about this exact question, but even the ancient Greeks, like Democritus, way before when, had the word atom, and he used it to mean something that is the ultimate indivisible quantity of which other things are composed of. Of course, he didn't have a very clear understanding of what that meant, he simply gave it a name. And then that name stuck, and then today it still means like a small constituent, but today we know it's no longer fundamental. In fact, we can break it apart. In fact, there is more elementary constituents. So the notion of what is the ultimate constituent really changed over the years as people realized that if I have something that I believe to be elementary and that has nothing inside it, it wouldn't take very long until somebody pointed out that in fact there is something inside it, and then that became somehow the frontier of what is the ultimate constituent. And then so it would go on and on and on. So there's like an onion with many layers, and people simply took out one layer after another. And so the concept of what was the particle that makes up this desk has different answers at different times of asking that question, and we'll see some of that at the very end of that series. Okay, thanks a lot.